So in this lecture, what we want to do is actually work out some of these problems. And again, the definition of the derivative isn't just replaced by the differentiation rules if you already know calculus. There are problems, for example, piecewise functions, where you have to use the definition, okay, where you actually have to use the definition. But let's look at some problems and try. So here's a definition. A function is said to be differentiable provided this limit, the slope of the secant slope function exists. It equals a number, and we designate that number, okay, slope of the tangent line, or dy dx, right? You're supposed to remember delta y delta x is what you get for the slope of a secant line. Well, dy dx again refers to that slope as a tangent line. We talked about that last lecture. And when you say x equals a, you're saying there's a point, right? It's a function, so if I specify an x value, because it's a function, by definition, there has to be a y value associated with that. So I have a point. So this is providing me the slope of the tangent line at that point. In point and slope, we have a tangent line, we have a linear approximation. Okay, and this is our secant slope function. All right, so let's just work some problems. I picked start out with an easier problem. Okay, they'll work up in difficulty. So we want to determine the slope of the tangent line when x equals 1. Okay, so how do we begin? Again, the first problem I'll help more. It's always a good idea to define the function. Again, if there's any simplification that you need to do or anything that goes on, you should do it in this step, not in the middle of the calculus problem. So this is the basic thing. As I suggest, it's a good idea to see if the function is defined there, if you actually have a point on the graph. If you don't have a point on the graph, there's simply no point going on with the problem. There won't be a tangent line, there won't be a derivative. So you're done. It's just an arrow protocol. Of course, you're going to use this later in other calculations, but this just tells us the point we have, 1 minus 1. Okay, this is the picture. Next thing we want to do is let's determine the secant slope function. So I'll give you guys a moment. Why don't you pause and just substitute everything in and do the calculation and see what you get. Okay, let me proceed. I'm simply going to replace f of x by its definition, and f of 1 is minus 1. We calculated that earlier. So you just substitute in and do the algebra. And what you're looking for here is you need to cancel the x minus 1 out of the bottom, right? Or else you can't use the extension theory to evaluate the limit. So look for an x minus 1 in the top. So if you factor out the 2, you can find an x minus 1. You can cancel that out. Remember, it doesn't really cancel. It's equal to 1. And 1 times a quantity is that quantity, right? So, okay, it's equal to 2. And you can see that the original function is linear. Right, so our tangent, it's not surprising that the slope is everywhere constant. So pick any 2 points and connect 1 minus 1 to any 2 points, and you get a slope of 2, and that's what this represents. Right, so we expect it's consistent that the secant slope function is constant at 2, because everywhere, any secant lines you connect with 1 minus 1 to any other point has a slope of 2. Again, notice it's not defined at 1. By definition of the function, it's not defined at 1. Rise over run. Okay, so these are just the pictures we have. That's the function itself, and this tells us the slope of the secant line connecting this point to another point. Again, you should physically understand how this is working. Now we're just going to evaluate this limit, and again, try it. At this point, you should be very comfortable. This should be a very quick exercise. Okay, so I'll pause and go. Okay, let me start up again. Here's my secant slope function, and we can see from the picture, right, if you had a picture. The limit as I come to 1 from above is going to be 2. The limit as I come from below is going to be 2. This function is not defined at 1, but it doesn't really matter. The y values are 2 and 2. So let's make that precise, right? This is our function m. And again, I'm following the standard procedures that we follow. Is the limit point a equals 1, right? This is my limit point 1. In the domain of the secant slope function? No. So I can't use point continuity to evaluate the limit. right? So again, it's always the same. You always want to do limits the same way. And if I'm going to evaluate the limit, I have to use the extension theory. I don't have another choice. So my function m, secant slope function, I'm going to call the extension n, right? M and n, that's just it. The rule is the same, and I extend that rule to the entire real line, right? Whereas here it's not defined for the function m, it's not defined at 1. So my extension just fills in the hole, right? And then we evaluate it. Now 2 is a 0th order polynomial, right? It's a 0th order polynomial, so it's point continuous when a is 1. So we're in good shape. We check our protocol. Do the two rules match between the function and its extension? Yes, they do. And it's a polynomial, and so it's point continuous. Check. So I can use the extension theorem. Again, I'm checking the boxes to make sure I can use it. So by the extension theorem, the function m and m have the same limit. N is continuous, so I can just plug in by the definition of point continuity. And then I evaluate the function n at 1, when x is 1 and it equals 2. In fact, it's 2 everywhere. And that's it. By definition, the slope of the tangent line when x equals 1 is the limit of the secant slope function at x approaches 1, and that's 2. So the next question then would be find the tangent line. So again, practice this. So let me do it. Again, hopefully you've done it already. Okay, I have my function. I'm just repeating it because I have a new slide. I mean, of course you have it on yours. This is my data. This is better organized than my last lecture. I have a point and I have a slope, right? I have a point on the graph and I have a slope. That's my data, and we're always going to do this, so it's very efficient. Tangent line, y equals mx plus b, right? I don't need point slope, it's no better. Y equals mx plus b. Plug in your slope, 2. Plug in your xy data, x is 1, y is minus 1. Solve for b. And there's your equation of your tangent line. Notice it's the same, right? Because the original function is linear. So the next question is determine the linear approximation. And again, if you haven't done it, pause and do it. Write it down. Okay, the tangent line is y equals 2x minus 3. So the linear approximation is 2x minus 3. Only, again, it's a function, so I've been sloppy about this, so it has a domain and a set y. And the range is contained in there. In fact, the range is the real numbers too. It's just, again, it's the functional form of this equation. That's all it is, and L for linear approximation. And again, if you look at the picture, it's an excellent approximation because the function itself is linear. But I just wanted to start with a problem where the algebra wasn't too crazy. So let's pick one where a little more realistic. But the steps are going to be exactly the same, right? Here's one. Why don't you give this a try? And again, the only place you're going to have any issues here is the algebra in terms of coming up with the extension. So it's not the calculus, it's simply the algebra. So again, jump in, give it a try. Okay, let me start up again. Again, I'm defining the function. Notice the function is not defined at 0. So there's not going to be any point there, so there couldn't be a tangent line, and we're not asking for that. We're looking for it at when x is 1. But again, these are things that you notice. If you're writing a program, a code, you have an error protocol. Evaluate the point, right? Evaluate the function 1. That, in fact, gives you the point that we're going to use later as well, right? That gives me the data for the tangent line. So I have the point on the graph. Now I'm going to do the secant slope function. Again, if you haven't tried it, give it a shot. Okay, let me plug in the data. Sorry, I went too fast. So my function, f of x is 2x. That's the rule. I just plug that in directly, right? Just plug that in. F of 1 is 2. I just plug that in. And now you see everything has to simplify. If I'm going to use I can't just, of course, plug in using continuity because we're not defined. But if I'm going to use the extension theorem, which is my only other tool, I need to cancel x minus 1 out of the bottom. So you just have to do the algebra until you get that to cancel out. I put a lot of steps in here. Maybe you don't need that many. But remember, the more steps you leave out, the more higher the probability of a mistake. So what I did here is I just simplified the top and I put in all the steps. And again, I put all the algebra rules I used on that crib sheet on the first page. So if you're struggling with algebra, just follow along and see how I'm doing. Again, there's no shame in working it out. But if you just do the algebra, what I did was essentially, well, you can see it. I mean, you can see it. Okay. So at this point, I'm going to simplify, and there's the algebra involved with simplifying this. I mean, it's a lot of work. I mean, again, what makes these problems difficult is the algebra, right? I mean, that's what I think. It's not the calculus, it's the algebra. And if you were very good at algebra, you know, this shouldn't be that bad. But again, a lot of people struggle with that, so don't feel bad about it. Just keep practicing. You're only going to get better if you practice. So it comes down to actually a nice simple expression, right? I mean, after a lot of work, it comes down to a relatively simple expression. Notice it's not defined at 0. It's not defined at 0. The function wasn't defined at 0 either, right? So you don't expect the secant slope function to be defined there either. And it's also obviously not defined at 1 from here. Okay, so we have the secant slope function. But notice the difficulty here was really algebraic. It really isn't calculus. Once we have the secant slope function, we can then evaluate the limit. And I just took the time to draw a picture here. So notice my function looks like this. This is the point we're interested in, right? The point 1, 2. This is the point we want the tangent line about. And this gives you the green, this function m, gives you the secant slope, right? It gives you the slope of the secant line. So this point's fixed. If you took 3 and calculated, there's a secant line that connects those points, calculated its slope, that would be this number down here, right? So notice if the function isn't defined at 0, neither is the secant slope function. But notice also that the secant slope function is not defined at 1, and this will always be the case, right? So there's a picture. So what we want here is the limit as x goes to 1 from the left and the right from the secant slope function. And from the picture, we can see that it's going to be minus 2. So let's just check it, doing it correctly. So I've just repeated the graph here and written the function. And you do this, it's going to be the extension theorem, but you go through the normal steps. Here's my function. Is the limit point in the domain? The limit point is 1. Is that in the domain? No, it's not. This function is not defined at 1, so I can't use the point continuity approach, right? That's what I'm getting at. So I have to use the extension theorem, okay? So if my function is this, I need to get it to work at 1. Notice it doesn't have to be defined at 0. I'm only taking my limit at 1. I just need the extension to be valid at 1, right? Because I'm going to plug in at 1. So again, the extension extends the rule to 1. That's really what I'm looking for. And again, I'm just going to now check that everything works. This function is a rational function, right? It's a polynomial over a polynomial, and rationals are continuous where they're defined. So in particular, this function is going to be point continuous at a equals 1, when a equals 1. Right, now I'm going to check the boxes. The two rules agree as long as you're not at 1 or 0. Right? So we want it to agree to the left and the right of 1. Our extension is a rational function, and so it's point continuous at 1. And so just apply it. It's in a generic way because of because of the extension theorem, their limits are the same, and is continuous at 1, so I can plug in at 1. And then I just evaluate the function. There's a typo. This should be n. Right? I mean, obviously I copied it from the previous slide. The function is n, right? N is minus 2 over 1 is minus 2. A lot of typos, but well. Okay, so I found the slope. The slope of the secant line, right? X equals 1. So at that point, the slope is minus 2. And then the next question, and see if you can do it, is find the equation of the tangent line and the linear approximation. So again, try that. That shouldn't take more than 30 seconds. Give it a shot. Okay, let me do it. We're going to find the tangent line. I'm going to, again, I'm just rewriting the function, right, so you have it. But my data is the following. My point is 1, 2, right? This is my data. I need a point and a slope, and my slope is -2. We calculated that in the previous example. Y equals mx plus b. I substitute in the slope. I substitute in my point data. And I solve for b. There you go. Y equals -2x plus 4. Okay, and then the linear approximation. You just convert the equation of the tangent line into a function form. And there you have it. And if you can draw the picture, it's nice to check, right? Notice if I have a slope of -2. Well, look at this line. The slope is negative, clearly. Okay, so again, if you can draw the picture, it's a nice comparison here. And you can see, once again, in the neighborhood here of the point 1, 2, you'd have to take a pretty small neighborhood, but it's a good approximation. It can be as accurate as you want if you take a small enough neighborhood. And that's the idea. So again, that was a more challenging problem. And the reason it was more challenging was because of the algebra, I think, right? But again, I'm not putting the algebra on there. You need to practice the algebra if you're going to be better. And otherwise, I'm sorry, but every problem can't be like the first one, linear. Now the feature here is piecewise, right? So if the function is piecewise, the secant slope function is going to be piecewise. So give it a shot. Try to work this out. We did one very similar to this in the notes in the lecture last class. So try it. See how it goes. Okay, let me jump in. Here's my function, and there are no obvious simplifications. Sometimes there are. Right? It's always good to look at that. But there are no obviously simplifications. Again, there's one function. The function is called f. There's two rules. There's one rule when x is less than 1, and there's one rule when x is greater than or equal to 1. Okay, so let's go with this. I have a point. So everything is good so far. I have a point, 1, 2. 1, 2 lies on the graph of the function, and we're going to build a tangent line and obtain a linear approximation. And at this point, it's going to be valid in a neighborhood, a good approximation in a neighborhood. So now we're going to calculate the secant slope function. I just drew the picture here. This is the graph of f, and here's my point. Okay, and you can see there's, well, I don't know if you see, but there's one rule to the left of 1, and there's one rule to the right of 1. Okay, and you can see that the secant slopes, it better be positive because everywhere we're obviously going to have positive slopes. So the secant function is, I have to do it to the left. Why? Because the rule changes to the left and to the right. So on the left, for x less than 1, my rule is f of x equals x squared plus 1. Okay? And on the right, well, we'll do that in a minute. On the left, that's what I have, and f of 1 is 2. I'm just going to substitute these both in. And we'll simplify. We have to find an x minus 1 in the top so we can cancel it in the bottom. Right? So that simplifies and so forth. You can factor the top. X minus 1 over x minus 1 again is 1. Again, be careful about canceling. I mean, people lose a lot of points on exams because of that. 1 times the quantity is the quantity. Right? And that's it. So as long as x is less than 1, my secant slope function equals x plus 1. Now we'll do exactly the same thing on the right. And so on the right, notice the rule is different. If you haven't tried, try. And again, is x greater than 1? Because again, it can't, even though the rule for the function is greater than or equal to, the secant slope function cannot be defined in 1. So I just substitute in the rule, right? For x greater than 1, f of x is 2x, right? I have the data point, f of 1 equals 2, so I just substitute that information in, factor out the 2, perform the cancellation, or, and the slope function for x greater than 1 to the right there is 2. So, summarizing, for x less than 1, the secant slope function is x plus 1. For x greater than 1, it's 2. And I can represent that function in piecewise form as well, and I can draw the picture. Right, again, it's not defined at 1, so it shouldn't be defined at 1. Okay? And now you see we're going to take a limit, so we're just going to need a left extension and a right extension. But it looks like, looking at the picture, now you wouldn't always have the picture. It should be from the left, the y values go to 2, and from the right, they're always 2. So we expect the limit from the left and the right to be 2. And I drew the functions, and again you can see it's linear. The function itself is 2x. It's linear on this piece. So if you can connect our home point to any other point and draw a secant line, it's going to have a slope of 2, right? Connect this point and this point. Rise over run, the slope is going to be 2. Connect this point to this, the home point to this point, rise over run, it's going to be 2. And if you look down in this piece, it's not obvious. Maybe it's going to be linear, but it's you know. So again, everything seems to make sense. This graph seems to be consistent. Our secant slope function is consistent with the function. Again, it's good to always have an intuition about things. It's always good to have checks in case you're making mistakes. Now we're going to evaluate this limit. So again, I want to follow the same procedures. I'm not saying you need to write it down. What I'm saying is you should think these things. There's the definition of the function. Okay, I have it over here. But is the limit point in the domain? No, this function is not defined there, so I can't use point continuity. Right? Again, train yourself to think in a precise manner. So this is pure and simply a limit problem. Forget where it comes from. I'm just trying to evaluate the limit at this point. So I'm going to use the extension theorem. And I need to do from the left and I need to do from the right because it's piecewise. So my extension to the left, I'm going to take the roll to the left and I'm just going to extend it, right? I'm going to extend it to the entire real line. And then it's all, again, it just follows. My extension and my secant slope function agree for all x less than 1. My extension is a polynomial, right? And so it's continuous. It's point continuous when a is 1. So by the extension theorem, the two limits are the same. I can evaluate the extension because it is point continuous by plugging in the value. And it's 2. So again, you should see this over and over again. And this kind of calculation shouldn't take you a long time. I mean, really, 30 seconds. This should be very quick. And I do exactly the same thing now on the right. Right, I just define the extension. Again, the rules match and everything. So the rules are the same for x greater than 1. The extension is a polynomial. 2 is a 0th order polynomial, and so it's point continuous. I apply the extension theorem, which says the limits are the same. N positive is point continuous at 1, so I plug in, and I evaluate it, it's 2. So again, I have a left limit, a right limit. They're the same. So it follows by definition of the limit. Remember, when you write x goes to 1, you mean x goes to plus or minus 1. You just summarize this. So the slope of the secant line is 2. And now we could calculate the tangent line in the linear approximation, but we don't have any more time, and you should be comfortable with that at this point, okay? So try some problems. I'm going to do some of these, I believe, in the lab, so good luck with that.